All right, if you haven't figured it out, it's chapter 13. We're going to run through A, B, C, and B and C real quick. And I do mean run because this should not take us 10 minutes. We're going to do a lot of practice in class. Note, if you want to be good in class, when we start ray diagrams, you should probably bring at least 3 or 4 colored pencils. And I would say of the people that are still using pen for physics, I would say bring a pencil for this section because you're going to do a little bit of erasing. And if you're really bad, you'll do a lot of erasing. You'll figure that out as we go through, especially when we start ray diagrams. So let's get right to it. First thing you'll notice, if PowerPoint wants to work, that's our stuff we're going to cover. Really, we're going to spend a lot of time on flat mirrors and curved mirrors, not so much characteristics of light. You guys have already dealt with waves. We'll jump through it. I'll make some notes real quick. You might want to watch the video 2 or 3 times just to catch up on everything we're saying. I'll try and emphasize things that are going to be really important as we go through. So, electromagnetic waves, any light you use, any radiation you use, there's always an argument of whether it's a wave, a particle, or what. Light is a form of radiation. It can be used as a particle or a wave. You'll see towards the end, we're going to treat it like a wave. In the beginning, we're going to treat it like a straight particle going in a straight line. You'll see that as we go through. You've seen this chart 1,000 times. Obviously, radio waves all the way down to gamma rays. Everything is either in nanometers, centimeters. I will tell you right now, you need to convert everything to meters. Convert everything to meters. Keep your life simple. If you don't know how to do the conversions, you need to come in and check with me. We'll get you straightened out. But you have to be able to convert from centimeters to meters, nanometers to meters, and do so quickly. So, first, frequency, speed of light equals frequency times wavelength. We always call this C equals lambda nu. C equals the speed of light, 3.00 times 10 to the 8th meters per second. If you've been with me a while, you understand that's not quite exactly true. It's rounded, 3 significant digits. It's what we use. We can jump through much more simply with using 3.00 than 2.99987 and 0.89 times 10 to the 8th. Again, 3.0, good enough. First idea is wave travels like a front. We'll use this example in a lot of different ways. The easiest one I use a lot of times is you're driving a car, the right side of your tires, example, drives off the road. Well, that pulls your entire car to the right. Why? Because that side of your car has been slowed down. It's the same idea when we start talking about waves hitting water or glass or any other medium that wave goes through. The Hughes principle, short version, it's a way to basically calculate where that wave front is going to hit and how it's going to move. That's all it is. It's just an approximation. We'll play with this a little bit more later on. Now, the idea here, they're getting really fancy terms. Short version, it's the density of light. If you think of it, take a flashlight. You hold it a mile away from something, you might be able to illuminate a house a mile away if it's a very good flashlight. As you get closer and closer, the intensity actually gets more and more. Why? The density of those light particles is shrinking down into something that's very focused. As in the picture, 1 meter, 2 meters, 3 meters. Obviously, the yellow light is very concentrated at 1 meter. At 3 meters, not so much. It's the density of light. Luminous flux is basically another way to do this. Lumens, if you've ever looked at light bulbs, you'll see lumens coming out. And that's all it is saying how many lumens. At, I think, light bulbs, I want to say is 5 feet, but I'm not certain. You can double check that if you want, if it's so desired. So, reflection, this is where we're going to spend a lot of time in doing reflection, ray diagrams, and so forth. Basically, reflection is nothing more than the change of direction of a particle. This can be applied to light, as we're going to do now. We also see it when we talked about waves in the last chapter. So, diffuse reflection, those 2 bottom definitions. Diffuse reflection is basically when you see a fuzzy image. Example, when you show light on a wall. Pretty much any wall is diffuse, it's got a texture to it. Specular, you'll never probably hear this term again, but it's just reflection. It's your shiny reflection. Basically, anything you can see an image in, i.e. a mirror, that's your specular reflection. It's what we typically use. Water is another good service, as a note there. This is where angle of incident, angle of reflection. This is where we're starting using terminology that is actually important. Short version, if you have played a game of pool, basically you understand the ball comes in at a 45-degree angle, it's going to leave at a 45-degree angle. Angle of incident, incoming, angle of reflection, outgoing. So again, incident, incoming, reflection, outgoing. They have to be the same. It is never going to change. If you strike at a 45, you're going out at 45. You strike at a 10, you're going out at 10. So there's your pretty picture. Incoming light. Notice incoming light, angle of incident is your theta, angle of reflection is your theta prime, reflected, incoming. Your normal is your basically perpendicular line to the surface it strikes. Okay. This is where we talk about virtual images and real images. Virtual images are the same distance from the mirror surface. Okay, so example, you look in a mirror, you are typically, if you stand a foot away, your reflection is a foot away. That is a virtual image, never really displayed in a physical surface. Kind of where you stand with almost all of your mirrors. Another pretty picture. If you notice several things here, the 1 and the 2, we'll talk about those when we start drawing the diagrams. Also, a flat mirror, your H and H prime are your size. P and Q, we're going to talk about what those mean here in a minute. However, your angle of incident versus angle of reflection. Theta, theta prime. Yeah. All right. Let's talk about concave mirrors. Concave mirrors basically used to make a real image. This is not a virtual image, it's a real image. So basically, real image, that bottom bullet is very important. Rays of light pass through the point on an image. They basically can be projected. This is where holograms are typically used. Okay, this equation you have to get into your brain. Those top definitions right there. The distance from the object is P. So object distance is P. Image distance is Q. Focal length is F. So 1 over P plus 1 over Q equals 1 over F. Make certain to get this in your notes. We'll use the math, but the short version is I wouldn't have picked those letters either. It's okay. So image distance is Q. Object distance is P. And focal length is F. Get it down, have it done. Another equation that you want to use is M equals H prime over H equals negative Q over P. Again, write that one down. It's fairly important. We'll get through quite a few calculations because you'll need to understand those in depth for your class. We'll play this in class when we start doing ray diagrams. Short version, ray diagrams is basically a way to check your calculations. We're going to spend a little bit of time on it. The idea is very simple. Actual practice is not. I'll be forthright. It's going to take a little bit of practice. I'm going to give you step-by-step instructions. In fact, they're attached to the the Canvas. And so you should be able to download them, print them off. Don't use them, rewrite them. It's important. I'll probably have you do it in class, but rewrite them in your own words. That way you make sense of it and you understand it, and not so much you can regurgitate. Regurgitation doesn't do you any good. So we're going to jump through those. We don't need to spend a lot of time on the calculations. We'll do those in class. I will tell you, you're going to do a lot of evaluation. Basically, hey, does this make sense? And that's where the ray diagrams are going to come into. All right, convex. I guess I should have clarified. Hopefully you understand what convex and concave is. If you think of concave, cave. Concave, in. Convex is flexing out. Okay? Concave is the easy one to remember. If you remember concave, you can remember the convex is that one that's outward flowing. So, and there's your lovely image. And we'll have ray diagrams to kind of help you out with all this stuff. So, that's your equation. I want to get through. Look, parabolic, we'll talk about spherical and parabolic. Parabolic's going to focus all of your rays. Spherical is not. Spherical is one of the problems you'll have because at the very edge, you'll start to fuzz out. We'll talk about this in very simple ways. You guys have already seen it. Let's get to the last section. Color and polarization. Color and very simple. You've already probably dealt with it in artwork. Everyone understands if I mix all my paints together, I make black. Well, you should make, but you make some brownish color. Now, works really well. So let's talk about additive primary colors. When we add colors of light, it's an additive color. So basically, when you add all the colors, you get white light. Again, this hopefully makes sense from physical science a few hundred years ago. When you sit there and put white light into a prism, it separates into the entire spectrum. White light equals all the colors of light. When you add yellow light, green light, blue light, all those colors, especially the primary colors, it will actually make white light. Now, one thing that I'll tell you, when you Look at the diagram. Looks pretty, and it should make sense. For light, make certain you understand light versus pigment. Last ones we'll talk about subtractive for pigment. This is what's filtering out the lights. That's the hardest part for people to understand. Pigments are actually taking light away. When you sit there and say, hey, look, it's a green leaf. Yeah, it's taking away all of the light except for green. Green is actually what's bouncing off. That's why I can see it as green. It's bounced off the leaf and it's hitting my eye so I can actually perceive the green. So pigments are subtractive, just like this. As we take out one, when we take them all out, it's black. So now here's where we get into the kind of theoretical polarization. This is actually a very good argument to have. You probably have used polarized lenses already, even though you don't wear glasses or maybe not had polarized sunglasses. That's the best argument for polarized light. Short version, everybody has seen a picket fence, right? So you take a picket fence, and I think it's the next diagram. Nope. Where'd my diagram go? Anyway, so picket fence. Imagine a picket fence. You take a hose, you can make a hose go through the picket fence, yes? Same idea applies. If I take that same picket fence and I try and wave a actual hose through it this way, it doesn't work. Why? The energy stops by the fence, right? Go up and down. Only light going up and down will actually go through the polarized light. That's one of the reasons why people use sunglasses. These are two polarized filters. They're both going up and down. So light that is going up and down can get through. Now you take the first filter and you change it the other way. So now you have a filter going that way, filter going this way, nothing's going to get through. If you don't believe me, sometimes when you're looking at your phone and you have polarized sunglasses on, it'll block them out. It'll block out all the light from your phone because the phone is actually giving you polarized light. So one of the big things I'll tell you right now, reflected light is polarized. Light can be polarized. Sunglasses help you do this. If you don't believe me, one of the things that auto industries has done is the light on your windows is typically polarized, but it's not completely polarized. We'll talk about that and why later on. All right, that wraps up chapter 13. It's a lot of information. You might want to read through this or listen through this again. Definitely take your own notes. If you haven't read the chapter, you should probably read the chapter and get that ball started as well.